So let's just start by quickly reviewing from yesterday, in your case earlier today, that the leading coefficient and degree tell us where a polynomial starts and where it ends. So remember that if it's an even function, it's kind of like a parabola. If it's positive, that parabola would open up. If it's negative, that parabola would open down. So remember that as you would draw these in, this one would go from quadrant 2 to quadrant 1, and so on. If it's odd, it's kind of like a line. An odd function that's positive goes up, so it would go from quadrant 3 to quadrant 1. And if it's an odd that goes down, it would go from quadrant 2 to quadrant 4. So again, you just kind of think about if it's a parabola shape or if it's a line shape, and if it's going up or down. Also remember that the constant tells us about our y-intercept. So the y-intercept on your graph would be the constant in your equation. The other thing that we discussed is our x-intercepts. So far, we know how many there are, because how many x-intercepts there are is based on the highest power. So this one would have a power of 1, 2, 3. So this would be a cubic function. And this cubic function would have 3 possible x-intercepts. So the issue is that we don't know how to find exactly what those x-intercepts are, because we have to factor this to find x-intercepts. So today what we need to do is learn how we can factor really large polynomials. Okay, so there's 2 theorems that we need to look at in order to factor a large polynomial. The first one is called the remainder theorem, and this is a fairly simple idea. The remainder theorem says that if your binomial is a factor, then the remainder is 0. So please highlight that part. But in order for something to fit perfectly into a polynomial, the remainder has to be 0. And think about that just like with regular long division. If it doesn't fit perfectly, there would be a remainder. There'd be something left over. So the remainder has to be 0 for this to be a factor. The factor theorem says that your binomial is a factor if you plug in the 0 and get 0. So let's look at what the factor theorem says in terms of this example. So to use the factor theorem and see if x minus 3 is a factor, I would plug in the 0. So what would make x minus 3 equal to 0? Positive 3. So what we're going to do, we're going to plug in x equals 3. X equals 3, and we're going to see if we get this equation to equal 0. If it does equal 0, then x minus 3 is a factor. So I'm just going to put a 3 in for all my x's. Okay, so when we plug in 3, we end up with that this equals 7. 7 is not 0. So what this tells us is that x minus 3 is not a factor. And it's not a factor because the 3 did not fit in perfectly to get a remainder of 0. We got a remainder of 7. Okay? Now, instead of the factor theorem, so you don't need to do these both, okay? Instead of the factor theorem, you could perform synthetic division. And remember that synthetic division is kind of like long division that only involves the coefficients of a polynomial instead of putting all the x's and stuff in there. So, synthetic division. Let's just go through that quickly. When you synthetically divide, you put all of your leading coefficients in the top. So here we have a 2 for the x cubed, a minus 9 for the x squared, a 14 in the x spot, and a minus 8 for our constant. You have a spot to write this on your page. You can write this in here. The number that we divide by is the 0. So I see that I have x plus 3 in my denominator, which means I'm going to put a 3 out in front. Because again, 3 is the 0 of x minus 3. And the process is, you start by bringing down your first number. So I bring down the 2. You multiply across. So 3 times 2 is 6. You add coming down. So minus 9 and 6 is minus 3 when you add them together. Then again we multiply going across. 3 times minus 3 is minus 9. We add coming down. So 14 and minus 9 is 5. We multiply going across. So 3 times 5 is 15. and we add coming down, so we get 7. But what does that 7 mean? That's my remainder, right? So, in order for this to be a factor, your remainder needs to equal 0. This one does not equal 0. So that means that x minus 3 is not a factor because the remainder is not 0. So it's not a factor because the remainder. One more theorem to note is called the integral zero theorem. This says that any 0 of a polynomial is also a factor of the constant term. So what that means is, in order for something to be a factor, it has to go into the constant term. So let's look here. Here my constant term was minus 8. So the only possible things that could be factors would be 1, 2, 4, and 8. 3 does not go into 8, so 3 is not going to be a factor. Okay? So that's what the integral zero theorem states, is again, it has to be a factor of the constant term in order to work and give you a remainder of 0. So here are the steps to factor a large polynomial. First of all, write out the polynomial. Step 2, you're going to have to find the 0 of the polynomial, and you can do this by subbing it in, like we did at first, where you plug a number in to your equation, so like this. You could do that to find your first factor, or you could use synthetic division to find your first factor, either or, but there's a little bit of trial and error with this step. So you're going to need to maybe try a couple different things to get a remainder of 0. Step 3, then you keep using synthetic division to find more factors. And once you get down to a degree 2, you can factor it normally. Like you can factor it using our normal grade 10 factoring methods. So let's try this example. It says factor x cubed minus 4x squared plus x plus 6 using the factor theorem. Now, again, I prefer using synthetic division. So step 1 says write it out. So we're going to write it out in function notation. So f of x equals x cubed minus 4x squared plus x plus 6. Step 2 is we're going to find some constants that are related using the integral factor theorem. So, right, what are numbers that go into 6? Because our factors have to go into 6. So we'd say 1, 2, 3, and 6. But be careful, you could also use the negatives. Okay? Negatives would also work. So also -1, -2, -3, and -6. So we have 8 options that would work for this polynomial. So we decided to try the factor of x minus 2, which means we plugged a 2 into synthetic division. When you go through synthetic division, you'll get a remainder of 0. Remember, that's a good thing. That means that x minus 2 is a factor. So far what we have is the factor of x minus 2, and then we have some other polynomial left. Remember, the numbers left over are the leading coefficients of the polynomial left over. So here we have a 1x squared, a minus 2x, and a minus 3 for a constant. Yep, so once we have this, now let's factor the remaining quadratic normally. So two numbers that add to get to minus 2, two numbers that multiply to get to minus 3, which is a minus 3 and a positive 1. Yeah. So my factored final version is going to be x minus 3 and x plus 1. So those are my 3 factors from the original equation. Now, how do these factors relate to the x-intercepts? Again, once it's factored, now we could look at x-intercepts. The x-intercepts are what make each factor equal to 0, right? So what would make the first factor 0? 2. What would make this factor equal to 0? 3. And how about this factor? -1. Good. So in this case, I have 3 x-intercepts, and now I know exactly where they are since I factored it. All right, here again, we're going to use the factor theorem to factor fully. Step 1, let's write out our equation. So 2x to the power 4, x cubed minus 13x squared minus 21x minus 9. So this one is a power of 4. How many possible factors could we have? 4, right, we could have 4 possible factors. So that was step 1. Step 2, we have to find the possible numbers that work. My constant is -9. What are the factors that go into 9? 1, 3, and 9. That's it. But remember, you can also have the negatives. So it could be -1, -3, or -9 as well. So we only here have 6 options that would work, and we probably have 4 of them that work, right? Because it's a power of 4. Okay. So next we're going to try synthetic division. And in synthetic division, we're going to put our leading coefficients of 2, 1, -13, -21, and -9. So we put our leading coefficients in synthetic division. Now remember that yes, I do like to start with 1s usually.
So -1 to start.
Sure. So let's try -1. So if I take, again, I'm going to try -1. I'm going to plug that in. Now when you plug the -1, you should get a remainder of 0. Remember, that's a good thing. That means that x plus 1 is a factor. So remember that -1 would be the 0, so x plus 1 would be the factor. But that leaves us with still a fairly large polynomial. So I see that I have a -9, which would mean we have a -12x, a -1x squared, and then a 2x cubed. So it should make sense that this is a cubic function, because we started with a function that's the power of 4, we divided out one factor, so now we're at the power of 3. So that tells me that I'm going to have to do synthetic division again. Yeah? The easiest way to do this is to just drop down another line from your table. That would be the easiest way. So a little trick that sometimes works is that when you find a number that did give you a factor, you could try that number again. So I'm going to try a -1 again, and now go through synthetic division, but with my new row of numbers. So again, so far we have 2 factors that are both x plus 1 from the 2 times that synthetic division worked. And then we can factor this last part just as normal by using regular decomposition. So when I use decomp, we should get the 2 factors of 2x plus 3 and x minus 3. So your new factored equation now has 4 factors in it because it was a quartic function, so a power of 4 to begin with.
So there's 2x plus 1.
For our assignment, we're going to start by doing these 5 questions using the factor theorem or synthetic division, and then a couple questions in your textbook.